So let's go ahead and continue with section 2.1, just do a couple more practice problems, feeling good about this, and then we'll start talking about 2.2. So I want to find the equation of the line tangent to the curve. So we have this rational function, and then we've got some x value of 4. So remember at this point, in order to do this, we're going to have to do the limit as h approaches 0 of the difference quotient. So at any point in time, if I'm either going too fast or going too slow, you can speed me up, you can slow me down, you can pause. So I am going to recommend that you pause at this point because we've already done some problems like this. So I'm going to pause, fill in a whole bunch of the stuff. So I would pause me while I'm working, you're working, and then go ahead and unpause it and see how you did. So as you can see, I plugged it into limit as h approaches 0 of the difference quotient. Showed my work, and then crossed out a whole bunch of stuff that went away with the orange. You see that green arc that I put in? It's just so I remember the stuff that I didn't actually lose in the process. Showed a couple extra steps just to make sure that I didn't lose anybody. So now we have the first derivative as negative 14 over 2x minus 3 quantity squared. So what we need to do, we have this x equals 4, so we need to do a couple of things with this. One, we need to actually find out what f prime at that value is so we can actually find the slope. So I think that's the first thing that I'm going to do from here. So taking my 4, go ahead and plug it in. And if I plug in 4, I think I get negative 14 over, the bottom gives me 8 minus 3, which is 5 squared is 25. So that's the slope at that x value on the curve. But as you know, we need to actually find the y that goes with this x that we have up here. So I'm going to go back up to the top where I'm circling my x equals 4, and I'm actually going to find the x value, the corresponding y value that goes with this from the original function. So I'm going to go ahead and plug in the 4. If I go ahead and plug in the 4, I think I end up getting 7/5. So 4 comma 7/5 is going to be the point from the actual f of x function. Now that I have the slope and I've got the point, I can just go ahead and plug it in. So therefore, I'm going to get y minus the 7/5 equals the slope that I calculated, which is that negative 14 over 25, and then x minus my x value at that point, which is 4. So that is the equation of the tangent line at the point 4 comma 7/5 on that curve. Okay, so continuing on to the next slide, we didn't really talk about linear approximation last class, so I figured I'd go ahead and slide it in here. The idea is if you know the equation of the tangent line in a curve, you should then be able to get like a pretty rough approximation to any value surrounding that point itself. So I went ahead and just I decided to do 4.1, which is pretty close to 4. So what I'm going to do is I'm going to take my equation from my previous slide. I'm just going to go ahead and write down here the one that we left off with. And I'm going to go ahead and manipulate this just so I can get the y by itself, so kind of in function notation if you want to think about it that way. So let's go ahead and move that to the other side. I'm really just getting it out of the way, that's all. And then from here, I'm going to go ahead and do my approximation. So I would say that the y is going to be approximately, because this is an approximation that we're doing, and I'm going to go ahead and just plug in the x now from here. So there's my 4.1 minus 4 plus my 7/5. And then honestly, at this point, I just went ahead and grabbed my calculator. So I plug this into my calculator, and it looks like the y value, or the function value at that point, is actually going to be approximately 1.456. So what I would say if I were to rewrite this, which I actually would, I would say f of 4.1, where f is my function value for this equation, is actually going to be that 1.456. So we can just use the equation of the tangent line at that point to give us an approximation for values around it. Alright, let's move on. Okay, so this is on the last page of the 2.1 notes, and it's pretty huge. So I went ahead and wrote it out here. My recommendation to you is to grab a highlighter at this point and actually highlight this stuff. So I'm going to go ahead and do that. So what we need to focus on here is we want to make sure that we keep this in mind, because as we go throughout the year, I'm going to talk about this, and we'll get into this in more detail later. So if function's differentiable at a point, then it must be continuous, okay? Function's differentiable at a point, must be continuous at that point. However, the converse of that isn't necessarily true, and we're going to take a look at some examples later that do that. So this is pretty huge. Definitely huge. And then you'll see in your notes that I actually have the graph of an absolute value function. So again, we'll come back to it, I promise, but it is one of the things that we're definitely going to be focusing on, but I want to make sure that we kind of establish that right now, since we have been talking about differentiability and continuity from the last chapter. And I think that that kind of seals it up for 2.1. So I want to go ahead and move on to 2.2, see if we can just get this started. So I'm taking a look at 2.2, page 1 notes. Up at the very top, we've got the first 7 rules for derivatives. I'm not going to read them at you. I know that you can. So I would probably pause right now, take a look at those if, so you have them in front of you. And I'm going to go ahead, so if I was doing the notes with you guys in class, I'd probably put these on the page 1 off to the examples that are already there. Kind of closer to the bottom of the page. So, again, go ahead, probably pause me, take a look at them, because I'm just going to kind of push my way through this. So, if we take a look at the first one, I have f of x as a constant. Now, if I were to think about what a constant graph looked like, so y equals 12. Y equals 12 is a horizontal line. When I have a horizontal line, so not that I'm going to graph this, but I'm thinking of kind of this little visual. So there's my y equals 12. Remember that the derivative is the slope of the tangent line at any point. But if I were to find a tangent line at any point on this thing, it would actually just sit right on top of that line. So what I want to know is the slope of that line. That's ultimately what I'm getting at here. So, but I know that the slope, so the first derivative, the slope of a constant, well, is 0, because a horizontal line, a y equals line, always has a slope of 0. So when I want to find the derivative of a constant, first derivative of a constant, it's actually just going to turn into 0. It's kind of nice, actually. Okay, number 2. So now I'm taking a look at that power rule, which is the second one down at the top of the page. We already discussed this just a little bit. So in order to find the first derivative, what we're going to do, and again, we can go through the whole limit as h approaches 0 of the difference quotient, go through and work it out. But here are those little shortcuts that I was talking about. So congratulations, we've made it. So what we're going to do is we're going to go ahead and grab the exponent and pull that down as a coefficient. We're going to keep our x, but our exponent is going to lose a power in the process. So for us, and I'm just going to go ahead and clean it up since I know that 3 minus 1 is just 12. And that's just going to give me 13x to the 12th power. Okay, should look pretty familiar. I think you guys discussed that at the end of pre-calculus last year, and I'm pretty sure we discussed it at the end of this year. So, same idea with number 3. If you have a number already out in front, a coefficient, then when you pull the 5 down, when you're trying to find the derivative, it's just going to get multiplied to whatever's out there, out in front in the first place. So if we go ahead and pull this apart, and remember, I don't expect to see, let's erase this little prime part. I don't expect to see you show me this step. I just want to make sure that I don't lose you in the process here. So f prime of x. So I just went ahead and pulled my 11 out. Now I can go ahead and use that power rule that we just did. So it's going to be 5x. That's going to lose a power, comes down to the 4th. But we can go ahead and just clean that up. So if I multiply these, I know that just gives me negative 55x to the 4th. So if you have a coefficient in front and you're going to do the derivative and you have an exponent when you do it, just multiply it times whatever's already out there in the first place. Okay, so number 4. So number 4 is the same idea, it's just a little bigger. It's not more complicated, it's just bigger. So if we wanted to go through and find the derivative, so I'm going to see if I can go straight to the punch on this one. So what I'm going to do is I'm going to take that 6 and I'm going to multiply it times the coefficient that's already in front there. So that's going to give me 18, but then my exponent is going to lose a power of 1, so it's going to come down to a 5. I'm going to do the same thing with the next one. So I get a negative 4 times 10, which is 40. My x loses a power, goes down to a 9. Likewise with the 7x squared, that's going to give me a positive 14. My x squared loses a power, and when I do that, it's just going to be x to the 1. Well, I don't really need to write that because x to the 1 is just x. Now, 9 is a constant. If remember, whenever we're finding the derivative of a constant, this actually turns into 0. Now, it's not necessarily the case where we actually have to show, actually I wouldn't even show that 0 if I were you. So I realize that that's 0, but when I write down my problem, I'm actually not going to include that. That's not necessary. And that's my first derivative for that guy. So let's move on to 5. So 5 and 6 have to do with sine and cosine. And we're actually going to talk about the other trig functions a little bit later too in this chapter. But the foundation of them is going to be the sine and the cosine. So I want to make sure we got a pretty decent understanding on that one. So same idea here. We've got a -2 out in front. So let's go ahead and just separate those guys. So it's going to be -2 times sine x. And since this is multiplication, I'm going to do -2 times whatever the derivative of sine x is. Well, if you take a look at your notes, up at the very top, like 8 spots down, maybe you've got the derivative of sine is cosine. So this is going to give us -2 times cosine x. Oh, that's f prime. Put that prime on there. So then f prime is going to be, we're just going to go and smush these guys back together. So -2 cosine x. Likewise on number 6, so same idea here. I'm not going to separate them this time. Actually, I will because I don't want to lose you. So I'm still going to have my 3 times my cosine x. Alright, well, if I want to find the derivative, I keep my coefficient times. The derivative of cosine is negative sine x. I'm just going to put parentheses around that guy. So I can go ahead and push these together as well. So if I do that, I get -3 sine x. So on this slide, we've got some examples that cover, I know it's the 7 first derivative rules, but I figured with number 4, I could kind of put the addition and subtraction together. So hopefully this isn't an issue. So again, if I go too fast or too slow, slow me down, speed me up, pause me, do whatever it is that you need to do. You can even rewind. All right, let's move on to the next slide. Now, this isn't in the notes, but I thought this was something that was important. Because again, it's not about being able to necessarily do the problem. It's important that you understand what you are doing or why something works. So I started thinking about if I was in class, what I would probably get the blank faces on and what the confusion would be. And it would be, how did you magically come up with the derivative of sine x? So kind of the same with cosine x. How did I get negative sine x? So I figured I would go ahead and just tackle one of them for you. So maybe you're not convinced. That's basically it. So what I would like to do is I'd like to actually just take a look at f of x is equal to sine x. So let's go ahead and deal with that. Now, I know what the derivative is because I told you what the derivative is, but I want to actually show you why it actually works. So what I'm going to do is I'm going to do the long way, so the limit process for limit as h approaches 0 of the difference quotient for that guy. So I'm going to go ahead and do my f prime of x. Remember to be super careful with your notation here. So I'm going to do the limit as h approaches 0. I'm going to do my difference quotient. So remember, it's f of x plus h minus f of x all over h. Okay, so on first glance, it looks a little overwhelming because I don't see any cosines in there at all. However, if we remember a little bit of our trig knowledge, we should actually be able to boil this down into what we're looking for. So the first thing that I am going to do is I'm going to tackle this sine of x plus h. So this whole business right here. That is the sign of a sum. So I'm actually going to do the sign of a sum formula. So it is the sine, cosine, cosine, sine. So probably one of the formula sheet problems that you guys had last year. So it is sine of the first times cosine of the second plus, so remember if this is sine, you actually match that plus sign inside. So sine of the first, cosine of the second plus cosine of the first, sine of the second. Okay, so this highlighted business, that is the expansion basically of that sine of x plus h. And then I'm just going to bring everything else down with me. Okay, so it doesn't look spectacular right now. I realize that. We're going to clean this up a little bit. So what I would like to do is I'd like to pull a couple of these together because they have something in common. So if I actually take a look at this sine x cosine h plus cosine x sine h minus sine x, I see a couple of things that I could actually pull together. So what I'm going to do is I'm going to go back and I'm going to look here. So at this piece here, I have a sine x. And in this piece here, I also have a sine x. Notice the other piece I didn't box doesn't, so it's not like I could take a sine x out there. So what I'd propose is that we actually put those guys a little bit closer together so we can do some factorization. And because I'm trying to show you something, prove something to you, I am showing a little bit more steps than I normally would. So I'm just going to go ahead and reshuffle some stuff here. So let's go ahead and just pull those guys closer together. Now, as long as you maintain the signs of the things that you have, you can shuffle as much as you want, just as long as whatever was positive stays positive, whatever was negative stays negative, and you're good. So I'm just reorganizing so I can put those guys together. All right. Because they have that sine x in common, what I propose we do is actually factor out what they have in common. Now, I know where I'm going with this, so instead of factoring out a positive sine x, I'm actually going to factor out a negative sine x. So what I'm doing is I'm focusing on these guys right here. So what I'd like to do is I will actually want to take a negative sine x out of there. So I'm just going to go ahead and factor it out. So if I take that out, I get my negative sine x. Now when I do that, I'm going to go ahead and pull it out of this first guy, or the second guy right there, so I can get a positive 1 to come first. Then I'm going to pull it out of the second one next. So this one here. So I'm going to take it out of the purple guy first, and I'm going to take it out of the green guy second. So what that does is it flips my signs, because if I took out a positive sine x, then it wouldn't flip the sign of these guys. Taking out a negative sine x for a reason, so stay with me, the reason is coming. So then just bring the next with me. Cosine x, sine h, not really doing anything with that right now, I'll get to it in a minute, all over h. Okay, this is not so bad. So I have used the sum and difference formula for sine, and then I grouped some stuff up together that both have signs in common. I factored out a negative sine x. Now, I'm going to actually break this up into two different fractions. So, remember that you can split a numerator, but you can't really split a denominator. Actually, you're not allowed to split a denominator. So I'm going to go ahead and pull these guys out separate from each other. Now remember, if you have addition and subtraction and you're trying to evaluate limits, you can actually just separate them from each other. So plus, now let's do the limit as h approaches 0 of the second part here. So cosine x sine h all over sine h. So all I did was split it into two different limit problems right now, but it is just splitting up a fraction. It's really all I'm doing. Okay, so my next step. Remember that I'm trying to find the limit as h approaches 0. Well, if there is stuff in here that doesn't have any h's on it, then when h approaches 0, it doesn't get affected at all. So what I would like to do is I'm actually going to take a look and see what I can take out. So I can take out of here, out in front. So it's not really an issue. So if I take a look at this very first part, this negative sine x doesn't have an h in it. So when I do as h approaches 0, it doesn't affect it anyway. And in the second one, this cosine x also doesn't have an h in it. And since these are strung together with multiplication within each of their fractions, I can't actually just pull them apart. So I'm just going to go ahead and pull it out front since it's not affected. So let's pull this negative sine x out of. Since it's not affected, it doesn't really even need to be in there. And then I'll do my 1 minus cosine h over h. And I've got my plus. Let's bring that cosine x out. So it's not affected, doesn't have an h in it, don't have to worry about it. Limit as h approaches 0. And then I can do sine h over h. Alright, I'm feeling better now. The only thing that's actually inside the limit process part of this is the stuff that actually has h's on it. Well, if you look very closely, very, very closely, these should look familiar. So if I take a look at this first limit, that limit is one of the corollaries for the squeeze theorem. So the limit as x approaches 0 of 1 minus cosine x over x. That should look very familiar. As a matter of fact, that limit, so let's go ahead and catch up here. So negative sine x is not affected. Just leave that out in front. But this we can actually do. By the squeeze theorem, that's 0. I don't even have to evaluate it. I know what that is. Plus, let's bring down that cosine x. That second one should look familiar also. So if I take a look at this limit as h approaches 0, and the green box, that is also one of the corollaries for the squeeze theorem. I think that's the one I actually proved, or offered to prove, depending on which class you're in. So I know that the limit as h approaches 0 of sine x over, limit as h approaches 0 of sine h over h is just 1. So here we go. F prime of x. Those cancel because that's just 0. Now I just get cosine x times 1, which is cosine x. Therefore, if f of x is equal to sine x, which is what we started with, then f prime of x is equal to cosine x. You can actually go through a process that is nearly identical to this to show that the derivative of cosine x is negative sine x. So, now you know. Alright, a couple more slides to go and we're almost done. So a little bit more complicated stuff, that's all. So what I would recommend, again, I'd recommend, is that you would pause me now, try these examples before I do them. Then, so I'm going to pause for myself, I'm going to do number 7, and then I'm going to unpause, give you an opportunity to take a look at it, and then pause yourself again for 8. So, again, my recommendation, remember you want to make sure that you practice these. Alright, so here we go for 7. So what I did from the first step to the second step is I remembered that if I have an exponent on the bottom of a fraction and I want to bring it up, then all I have to do is make sure that that exponent turns to a negative number. And then that allowed me to bring the x plus 4 up to the top. Now I'm okay to just go ahead and do my rules. So I took the negative 3 exponent, I multiplied it times the 3 halves out in front, kept the x plus 4, and then remember that you're supposed to diminish the power by 1. So if it's negative 3 and you subtract 1, you do get negative 4. So again, I would pause me right now if I were you. I'm going to go ahead and work out 8 on your own and see if we match. Alright, number 8. So kind of like on number 7, I remembered that if I want to move something from the bottom of a fraction to the top of a fraction, all I have to do is change the sign on the exponent. Well, I went through on this one and I remembered that if I have a root, I technically have a rational exponent, so a fraction exponent. So I just went ahead and rewrite it with a 1/5. Now that I have it rewritten with a 1/5, I can go ahead and do the exact same process. So bring that coefficient, bring that exponent down, multiply it times the coefficient that's already there. There's nothing there, so it's just 1 times 1/5, which is 1/5. And then remember to decrease your exponent by 1. So 1/5 minus 1 is actually 1/5 minus 5/5. That's where I got my negative 4/5 from. So again, I'm going to go ahead and move on to 9. So keeping in mind that if I have a single denominator for a whole bunch of different pieces of numerator, I can actually just go ahead and divide them. So I broke these down into 3 separate fractions. So I did x to the 7th over x cubed. Remember, when you do that, you actually just subtract the exponents. So it gave me x to the 4th. Likewise, I did the same thing with the 4x to the 4th over x cubed. That's 4x. And then with the 2x over x cubed, I do get an x squared on the denominator, or in the denominator. Now, at this point, you can either just go ahead and bring it up to the top or leave it in the bottom. But on my third step, you see that I actually brought it up. So once I have it up, that negative 2 exponent, then I can just go ahead and do what I've been doing before. So you'll notice that I'm still just following the same pattern. So if I can keep everybody kind of on level ground, so bringing the x up from the denominator, getting rid of roots and leaving them as fraction exponents, then I can go ahead and just use the rules that we've been talking about in this section. Okay, let's go ahead and try 10. And try 10 is a lot like one of the examples in your notes. Now I'm going to show you one way how to do this problem, but we're actually going to do this another way in another section, just so you can see there's multiple ways to do it, and then whichever way you want to do it is perfectly fine with me. So continuing on with number 10, so the one way that I'm going to show you this time, and it's in the notes this way too, is using the idea that we know squared is times itself. So I went ahead and wrote out both of the 3x plus 1s, and then I went ahead and just multiplied it out. Now that I don't have anything trapped inside parentheses, I can go ahead and continue on in the same fashion that I have for this section so far. So then I just went ahead and used the rules that I normally would. Now, again, keep in mind, I am going to show you another way to do this in a future section. Either way, you're going to be fine. Just as long, both of the answers are going to be equivalent, so it's not a problem. Okay, so let's go ahead and evaluate the derivative of that when x is equal to pi over 3. So the first thing that I would do if I were you, which is exactly what I'm going to do, is I'm going to go ahead and just do f prime of x. I'm not going to do it the long way, not the limit as h approaches 0. I'm just going to go ahead and use my shortcuts. I know that the derivative of sine is cosine, and I know the derivative of cosine is negative sine. So that's the first thing that I'm going to do. And I am going to kind of go straight to the punch on this one, even though I do have that coefficient out in front, but it really shouldn't be a problem for us. So if I have negative 2 sine x, the derivative of sine x is cosine x, so I get negative 2 times the derivative, which is going to be cosine x. Then for the next part, I've got cosine x. Well, the derivative of cosine x is actually negative sine x. Okay, so there's my derivative. Now what I want to do is I want to evaluate that at pi over 3. So all I'm going to do is just go ahead and plug in pi over 3 to these things. So we do need to know, remember, it's just a little bit of trig knowledge from last year. You're going to do a little bit more trig in future math classes, but in this one we just need to make sure that we know the basics, especially with the unit circle. So if I do f prime of pi over 3, I know that I'm going to do negative 2 times, okay, cosine of pi over 3, first quadrant, pi over 3 is fairly tall because it's a 60-degree angle, which means that the adjacent side is pretty short, so that's going to be the half. Minus sine pi over 3 still, first quadrant, 60 degrees, fairly tall. The opposite side of that is actually going to be root 3 over 2. So I'm going to go ahead and clean it up. I don't necessarily have to, but I may as well. I know that the negative 2 times a half is negative 1, and then I'm just going to subtract the root 3 over 2. I'm perfectly happy leaving it like that. So I went through, found my derivative, and then just plugged my numbers in. Notice that I'm not having to do the limit as h approaches 0 anymore, the difference quotient. It's a beautiful thing. Please keep in mind, though, that that doesn't mean you throw away that knowledge. There may or may not be some questions in your future where it says you have to use the definition of the derivative or the limit process to be able to evaluate. All right, last slide. So we're going to find the equation of the tangent line to f of x is equal to 3 over x minus 6 when x is equal to 4. So what I would like you to do, go ahead and pause. We should be able to do this. I would like you to, well, we want to find the equation of the tangent line, which means we need to find the slope of the tangent line. To find the slope of the tangent line, we need to find the first derivative. So let's go ahead and find the first derivative. It's the very first thing we should do first. Go ahead and pause me now. Let's find the first derivative, and then I'll check back in with you. All right, so I moved the x minus 6 up. Since there was no exponent on it, the exponent's a 1. So when I bring it up, it's a negative 1. I went ahead then and did my first derivative. So I times the negative 1 exponent times the 3 coefficients where I got my negative 3, kept my x minus 6 with me, and then diminished the exponent by 1, so it's negative 2. Now, I'm perfectly okay leaving it like that, but I'm going to have to plug a number into it pretty soon. So I think it would be a little bit more manageable or make more sense if I put that x minus 6 on the bottom so it becomes a positive exponent again. Okay, so now we have a couple things we need to do. we need to evaluate f prime of x when x is equal to 4. So let's do f prime of 4 now and see what we get. So with f prime of 4, if I plug that in, it looks like I'm going to get negative 3 over, where 4 minus 6 is negative 2, negative 2 squared is 4. Okay, so that's the slope. This is the slope of the tangent line at x equals 4. But remember, we actually have to find the point. So I'm up in the top right-hand corner now. I know that I've got my x, which is 4. But to find the y that goes with it, I actually have to plug it back into my original f of x function. So if I plug my 4 in there, I think I get 3 over negative 2, which is just negative 3 halves. So there's my actual xy point. All right, so now that we have that, I can use, go ahead and highlight what I'm using, my 4 negative 3 halves, and then my f prime is actually going to be negative 3/4. So now I should just be able to pull it together. So the equation of my tangent line at that point is going to be y minus y1. Well, it's negative 3 halves, so let's make it positive 3 halves. So plus 3 halves is equal to the slope of my tangent line, which I calculated to be negative 3/4 at, and my x value was 4, so x minus 4. So right there is the equation of the tangent line to that original curve f of x at the point x equals 4, or when x equals 4 at the point 4 comma negative 3 halves. And I think that sums it up for this section. So, or excuse me, for today. We'll continue this section next class. If you have any questions, make sure you write them off to the side. I'll be back in class next time. And then if you have any additional time at the end, go ahead and work on your assignment for this chapter, for this section and the previous section.